All right, 5.7, we're estimating probabilities using simulation. With simulation, for some reason, AP really likes to do these. And so I'm going to give this, I'm going to go 3 stars, maybe 3.5 stars. It's likely, about every other year, there's a simulation question. Okay, and what is simulation? Simulation is the process of synthetically generating observations in a simulated model that is similar to the real situation of interest. So it's just using computers and random number generators to make instances so that you can do the long run relative frequency of the probabilities. So you're going to use simulations when observational real data is not available. All right, I'll show you an example on the next page of something like that. How about if there's time and resources to gather real data is not available? So like you need this by tomorrow. You want to find the probability tomorrow. All right, but you can't gather real data by tomorrow. It might take months, if not years, to get the real data. Or just that it's impractical. So these are reasons why you might use simulation. And so how does it work? So basically you design an artificial model that represents the real situation, where you can generate observations synthetically, and you're doing this by random number generating. So you're going to use a random number generator to get your instances. Generate an observation with a random number generator or table, and you're going to repeat step 2 for a large number of times. Now, because we have computer programs, I mean, you can get millions of instances within seconds, if not minutes, or minutes if not seconds, because our computers are so fast. And so this is used quite a bit. All right, random number generating is an important part of this. You know, we do that in sampling in chapter 1. Remember when we talked about sampling, and every question had to have some discussion about random number generator. Same with simulation. You have to say you're getting your instances using random number generator. So there are programs out there, like there's a website called random.org where you can put the parameters in and it'll just generate you a random number. You can certainly do that. Or you can use tables, and these tables are random numbers generated from some random number generator program. Now let's take a look at this here. So you'll see that there's rows of numbers, so you can communicate which row of random numbers. And it's not 89,329. It's just 89392 with a comma in there, so you can easily just read the numbers in there. And sometimes you want to generate a number between 1 and 10, so you use single digit numbers. And sometimes you want to generate a number between 1 and 100, or 1 and 99, or 0 and 99. And in that case, you'll use 2 digits. So you'll use 89 first, and then 39, and then 22, I guess, and then 32, and then 12. There are times where you need 3 digits, and you'll use 3 digits. So 893 might be your 3-digit number, and the next one would be 922, and so on. Okay? All right, am I doing something? Okay. All right, so this is a random number generator. Table. And so, okay, so let's go ahead. Oh, here. Although technology is used to carry out simulation and practice, on the AP exam, random number generators are used. Random numbers are often used so that student responses can be evaluated consistently. So they don't want you to generate your own random numbers on your calculator. There's programs that they can do that because they want you to use the table so that they can follow like the hundreds of thousands of students taking the test, so they have consistency in grading. All right, so you need to know how to use a random number table. All right. Here we go. Here's the example. I'm going to need your opinion here in a second. Let's say that a new bill was proposed that would impose a rule on families that they must continue having babies until they have a boy. Once they have a boy, however, they can no longer have another baby. Do you think they could actually do this rule?
No.
In America? Maybe elsewhere? Yeah. there's countries that probably try to do that. Wouldn't they're yeah they're yeah
Yeah, China's like a one child.
they yeah they the one China policy has been abolished. Um,
I don't keep up with China.
mainly well they had they're huge populations, but they mainly did it because there's an economic crisis coming around that there's not enough younger people to support the older generation getting into retirement. So that was just an unintended effect of the one child policy, because you have less than one kid, because not all of them make it to adulthood, to support two parents. So in our country, we just need you want to have the inflating populations so that you have enough generations coming up underneath to support your older generation over time.
I heard that the ratio of adult diapers to baby diapers is bigger than one.
Okay.
I heard that.
All right, so let's recap this.
That statistic to like determine that the population was growing older and like there was less young.
So there were more adult diapers.
Yeah.
Then diapers. Okay, depends. Come on.
I mean in Japan.
Okay,
That's-
sorry. Depends. Depends. That's what they're called. Adult diapers. They're called depends. Come on. All right, get the joke.
Oh, you said depends.
All right. All right. So here we go. So they have a rule. Let's make sure you understand it. You have to have a kid. You have to have kids until you have a boy. So it's basically however many girls you have until you have a boy. And once you have a boy, you can no longer have any more kids. All right. So you look back on the reasons for doing simulation, you'd find out that this is impractical. It's not legal. You can't really run it. It would take forever. Like, how long would it take for you to wait for actual families to have kids until they have a boy? I mean, it'd take 20 years, 30 years to run an actual study. So what we'll do here, first off, would this whole situation, you have to have a baby till you have a boy, and then once you have a boy, you can have no more kids. Would this change the proportion of boys in the population?
Yes.
Give me an answer, everybody.
Yes.
Okay. Which one would be larger?
Girls. Or whatever they
Okay. Girls, you said? Or boys?
Girls.
Okay, so you guys, raise your hand if you think the girls will be a higher population. Okay, raise your hand for the boys.
Actually, nah, I don't know.
Okay, just one? Okay, so one for them and infinity for girls. Okay. All right. Okay. All right. First off, what's the probability of having a boy? Yeah, so we'd say probably is 50%. Now, I'm sure it's not exactly 50%. I'm sure it has to do with like the number of X or Y chromosomal sperm.
Yeah.
And all right, 50% is good enough. Okay, 50% is good enough. Okay. Can we collect real data on this?
Yes.
Good Lord, no. Okay. All right. All right, so here's how we're going to do a simulation here. We're going to simulate this situation using the probabilities, and we're going to generate single random numbers, and when the random number comes up even, we're going to say it's a boy, and when it comes up odd, we're going to say it's a girl.
Can you switch me to the boy side?
What?
On what would change the proportion of the boys in the population?
Okay, so still infinity and 2. So we got 2 now. All right. Kairos, can you do a favor for me? 1 through 4, can you give me a random number? Give me a number, 1 through 4.
3.
Yeah, I knew you'd pick 3. Perfect. Okay. I should have. Okay, all right.
Oh.
Okay, we'll go 3 here. This is just a number to be able to communicate with somebody else. Which row of random numbers you're going to go with. Okay, so I'm going to need some help here. We're gonna do 20 trials of this simulation. Once you have a boy, the trial's over. So here we go. So the first number is a 1. Is that a girl or a boy? Girl. So we have to have another kid. The next number is 1. Is that a girl or a boy? Then we have a 4. Girl or boy? Boy. All right. So that in.
Trust the process.
Okay. So that right there, that's one instance of the simulation. So that simulation number 1 is done. Let's go to simulation number 2. The next number is 5. Girl or boy? Out loud, guys. 2. Okay, we're done. 3. Sorry. 7. 4. Let's go to step 4. 1. 9. 7. 8. It's like my family growing up. 3 sisters and me. Okay. Yeah. All right. 3 girls, 1 boy. Yep. Do you pick on your brother? Yeah. Like my sisters did to me. They always picked on me. My sisters were just, they were all older than me, picking on me. Okay. Okay. You know what they told me? So I had 2 uncles. My mom had a brother and my dad had a brother. My sister told me, guess what? You're the only one in the family without a brother. And I cried. That's the type of things that they would do to me. You're the only one in the family without a brother, and it was true. All my sisters had a brother, and both my parents had a brother. This is mean. Okay. Okay, here we go. 1. Girl or boy?
Girl.
9.
Girl.
6. Ooh, so you guys think the girls are going to be more, huh?
No,
Looking.
I'm sticking with my gut.
Okay, 2.
Look at 6. Don't go.
4.
Trust the process.
4. 8. 4. 4. Okay. Let's go to trial 11. Here we go. 3.
Girl.
9.
Girl.
0. 3. 6. 0.
Boy.
2. 6. 4. 8.
Gotta trust the process.
0. 7. 3. Oops, sorry. 2. I don't even. Here we go. 12, 13, 14, 15, 16, 17, 18, 19. Okay. 3. 1. 3. 7. 7. 7. Good luck finding a bathroom in this house. Okay. 4.
This is one crazy family.
Okay.
I think that's 20.
This is one determined family. Like, we're getting this boy. Okay. All right.
I still think the boys.
Okay. So we had 20 trials. So what are the total number of boys?
I got my bet. 3.
Total number of boys, guys. Yeah, because that's the max you could have because,
You have to stop once you get one.
yeah. Girls, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
Wow.
What?
Trick question.
Okay, I didn't pick the number line.
If we if we didn't do 19,
You?
if we didn't do 20, the boys would have won.
What's that?
If we didn't do if we didn't do 20,
So what's the probability of a boy? 20 out of 40 equals 50%.
what?
Does this change the number of boys in the population? No. And this is the short number, but I mean it's a small number of instances, but we could easily create a program. I mean, Luke, could you create a program here to run this 1,000,000 times? Yeah, it wouldn't be that hard to write it, and so we would know right away. This is how they make decisions. A lot of policy-based decisions at the federal levels. They run simulations to see what they think it'll happen. Okay. Yep. Maybe they should have done that on whether or not we'll have inflation. All right. Okay. All right. I think they figured that out. All right. Cereal boxes. Okay. Apparently they have toys in cereal boxes. We don't really buy cereal at our house. Usually we only get cereal when they come home in the RVs. People bring cereal, leave cereal boxes in the RV. But I guess they have toys. Do they still have toys? Are there like games to play on the back of the cereal box?
Yeah.
Okay.
Sometimes, like crossword puzzles,
Yeah.
mazes and stuff.
So in the olden days, they used to have toys that you could get somewhere in the cereal boxes. And so one method for increasing the sale of boxes of cereal is to suggest to children that they collect a set of small toys. So they might be Power Rangers, and you want to get all 4 Power Rangers, or all the, I don't know, what is Spider-Man? What is he? All the Paw Patrols, yeah.
Oh, yeah.
Collect all of the toys, all right. All the Rainbow Brights, all right. Suppose that one of 5 different toys is put in every box, with the hope that the kid will have to buy at least 10 boxes of cereal to collect all 5 toys. One strategy the company could use is to distribute the toys, is to put, I guess, each toy in 20% of the boxes. Your task is to design a simulation that will be used to assess this strategy in terms of the number of boxes of cereal a person would need to buy in order to get a complete set of toys. All right, so the simulation is like, how many boxes will I have to buy in order to get all 5 toys? What's the minimum number of boxes do you think I'll have to buy to get all 5 toys? 5. So you could get lucky and just boom, 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 5, you happen to get all 5. All right, if you get the same toy once, well then you have to buy another box in hopes to get another one. Another company that does this, does McDonald's still do the Monopoly days where you go buy something from McDonald's and you tear off a little tab and there's like a Monopoly thing on there? Does Albertsons do it? I know they've sold the rights, but McDonald's is the one who did it for the longest.
Happy Meal.
Yeah, there you go. Happy Meal might be. Okay, so you get the idea here.
Oh, Happy Meal.
So what we're gonna do is we're gonna assign digits that match the situation, which is around 20% in each box or each toy. So toy 1, we could do something like 0 and 1 could be our digits. Because I'm gonna assign enough, well, here we go, 2, 3, 4, 5, 6, 7, 8, 9. That's all the digits from 0 to 10, and each one has 20% of the digits. So it works out nicely here. All right, if I had 4 toys, it would have to be 25% of the data. If I had 4 toys, it'd have to be 25 in each one. Then you'd have to go to 2-digit numbers in order to get 25% in each one. So you'd have to go to like from 0 to 20. Well, I'll do that example here, but you'd have to change these to match the situation. Your biggest battle is coming up with a way to set this up for those probabilities to happen. All right, is everybody following on this example why we chose the numbers? Okay, use the random number table to run 10 simulations, we might not get all 10, to determine that doesn't make sense. The simulation, what's the probability of it taking more than 10 boxes? I must add.
80%.
Okay. So instead of saying more than 5 boxes, we're going to go ahead and say more than 10 boxes. Okay, because that's what it says right there. All right, so let's just start with row number 1 right there. So for simulation number 1, I'm going to tell you a random number, and you tell me which toy they got. So 4, what toy did they get? 5, what toy did they get?
3.
1. 8. 5. 0. 3. 3. 7. Okay. Did we get all the boxes? Okay. How many did this take? 9 boxes. Okay. 2. 4. 2. 5. 5 again. 8. 0. 4. 5. 7. How many boxes? Okay. 3. 8. 5, you said? 9. 9 again. 3. 4. 3. 5. 0. 6. Is that all of them? How many?
9 every time.
It's ended on 4 every time.
Wow.
These aren't random. 9 or 8.
5.
9. 0. 7. 2. 9. 9. 0. 4. Is that it?
Yeah, it is.
No, yes.
Yeah, it is.
1, 2, 3, 4, 5. Yes, how many? 1, 2. Dang. I did not plan this. Okay. This might be a busted example. How about 5? What's that? 3. 5. 7. 0. Sorry, no. 3. 1. 0. What's that?
Sorry.
Okay, 3.
That interrupts everything.
2.
7. 4.
3.
7.
4.
8.
5. That's all of them.
That's 10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Do we need to do 10 simulations, or are you guys following?
Yeah.
Okay. So for the sake of this example, I'm going to go ahead and say what's the probability that's greater than or equal to 10 given our situation. Okay? So the probability of greater than or equal to 10 boxes is going to be the number of trials that we did this, which is 5, and how many were over 10? 1. So it's going to happen, we'd say 20% of the time. Now, this is incredibly a low number. 5 instances isn't a lot. And so I wouldn't trust this, but like I said, you could write a program to do this, and you could have hundreds of instances pretty quickly. All right. And one way to look at this probability is to say, what's the probability of greater than a number? That's usually how they ask it. But at some point, you could like look at average, like what's the average number of boxes that we could expect for kids to purchase? And so they can find marketing models and say, okay, well, kids will lose interest if it's like 50 boxes, okay? but if you want them to buy more than 5 boxes. And so where's that sweet spot of kids actually doing this? Yeah.
No, it's just.
Oh, cool. All right. Here we go. Let's do this again. Suppose that the cereal box company decides instead to put toys in the boxes in a way that makes some of the toys harder to find. So our goal is to get more than 10, so their goal is to maybe make it harder to get the toys so we can get it over 10. Only 20% of the time it was over 10, so we're going to try to change it up here. So toy 1 will be put in 30% of the boxes. I changed it from 40 to 30. I did it for a specific reason. Toy 2 and 3 will be put in 20% of the boxes. And toys 4 and 5 will be put in 15% of the boxes. I think that adds up to 100, doesn't it? So for toy 1, we need 30 digits. So it's going to be from 00 to 29. For toy number 2, toy needs to be put in 20%. So this is going to be from 30 to 49, and then from 50 to 69. And then we got the 15s in these 2 boxes. So this is from 70 to 84, and from 85 to 99. I couldn't just use a single digit to make this situation because the probabilities don't divide into 10 digits. We needed more digits. If it doesn't work out to 100%, what you can do is run numbers to a point and then have some numbers that just are null. Like if you get that number, it wouldn't count. All right, so you'll see that too sometimes. All right, so let's run some instances of this one. Okay. On this one, we're going to run it. If we get 10 or more, we're just going to shut down the situation, because in this particular stat that we want, greater than 10 boxes, we don't care if it takes 60 boxes. We just care that it's more than 10. So once we get to 10, we can stop it and go into the next one, because it is over 10 at that point. All right, does that make sense? How you can kind of shortcut this one? If I wanted the average number of boxes, then I would have to carry it out all the way. But if I just want to know the probability of getting a 10, so let's go here. Situation number 1 here. I'm going to yell out the numbers. You guys write them down and tell me when we hit all of them. Okay, 94. 5. Is somebody writing them down? Okay, 60. 69. 78. 82. 52. 96. 01. Do we have them all yet? 46. That's all of them? Okay, give me the number sequence. 5.
3, 3, 4, 4, 3, 5, 1, 2.
Okay, how many did that take? Would you say 9?
9.
Okay, next one. 05. 66. 90. Is that 5? Doesn't matter. 93, 95, doesn't matter. 74. 46. 32. 06.
So that's all of them after 2.
You got them already?
After 5, yeah.
Oh, okay, so
It's 1, 3,
1,
5,
1, 3, 5.
4, 2.
Dang. How many is that? 5? Okay. 3. 08. 91. 91. 36. 18. 07. 17, 77, 29, 78, 75, 88, 69. Are we over 10 yet?
Yeah, 5 was 10. So 1, 5.
Oh, what did you get? 1.
1, 5, 2, 1, 1, 1, 4, 1, 4, 4, 5.
And that's 10.
Yeah.
What's that?
We still need a 3.
A 3 at the end?
Well, that's above 10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we're already at 11. You can certainly go on until you get all of them. Okay, if I was saving time on an AP test, if the probability they want is more than 10, we're already more than 10. So we could continue this, but it doesn't change the fact that this one right here is now a success. Okay, we've now gotten more than 10 for this particular kid. Okay, all right, so let's go to 4 here. So which one did we leave off on? It doesn't matter. Okay, so 84. Do you say 4? 10. 61. 30. 97. 33.
That's all of them.
That's all of them?
After, it's,
That's 5 boxes.
yeah, 4, 1, 3, 2, 5.
4, 1, 3, 2, 5. This is interesting. We changed the probability where it dropped the probability in some toys and increased it on one toy, and it's not, seems like it's a little bit better, right? Because we have 2 times where it took only the minimum number. All right, so set 5 here. You ready? 66, 04, 18, 32, 67, 68, 22, 36, 21, 30, 22, 66, 97, 02.
We're at 10.
We're at 10?
Yeah, or past 10.
Okay. So go ahead and give me your numbers.
I have 3, 1, 1, 2, 3, 3, 1, 2, 4, 2, 1.
And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we're at 11. And we still didn't get it. So we could have continued this out. It might have taken a long time. This one would have gone a little bit further because we were just missing the 3. So 3 more boxes. So 14 would have been this one. But we stopped it because we wanted to save time. So now what's the probability that it's greater than 10 boxes? 2 out of 5. I honestly believe if you ran this one out for a long time, that these 2 probabilities would be different. Because it's following the probability of each box happening, even though it doesn't look like that much, or when you're only doing 5 instances of it, it's possible, it's likely that you could get the same scenario, especially since the probabilities aren't that much different. All right, does that make sense how that works?